We've been looking at some things that have electrical charge. Some of them have positive charge, some of them have negative charge, but the things that we've seen so far, the charge has stayed in that object. So now we're going to look and see what happens if that charge starts moving. So here we have this same device that I used before, that one side charges up with negative charge and one side charges up with positive charge. This time though, I put a wire between them. So the question is, if I had a positive charge inside this wire and I start cranking this, if this side turns negative and this side turns positive, what's going to happen to the positive charge in this wire? Well, is it going to stay in the same place? It's going to be repelled by the positive charge over here, and it's going to be attracted to the negative charge over here. So in the end, it's going to flow through the wire. Charges that are in the wire are going to start to flow. And so as I charge it up, we'll find that in the end, I'm not getting an overall charge on this, because as I build up extra positive on one side, then it's going to push positive through this wire, and it's going to come over to the side that's negative, and they end up just evening out in the end. Now, I could put something on here that has a little bit of resistance. I could put a light bulb on here, and then as those charges are moving through the wire, they could go through that light bulb and light it up. But for now, we're just going to talk about this. So a flow of charge we call current. So we started looking at how we could calculate with current and voltage and resistance. Current is flowing charge through a wire. Now, if we want to be consistent with our models here, we could say, what is it that's really moving through this wire? Is it positive charges? Well, no, we said actually it's electrons, right? So really, there are electrons that are getting pushed away from the negative and attracted toward the positive. That's what's really moving. However, back when Benjamin Franklin and his friends were making up this electricity model, they just randomly decided that they would call one kind of charge positive and one kind of charge negative, and they said, okay, let's talk about positive charge flow. So the standard way of talking about electrical flow or current is positive charge, the direction a positive charge would flow through a wire, even though it's actually negative electrons going the other way. If they had discovered electrons before their time, we probably would have done it differently. But that's what we have for now. Okay, so we can get a difference between these two sides, and we can say that there's a potential energy difference between those, because they have the potential to push charge between them. Oftentimes, we will look at what we just call potential difference. So, potential difference would be if I have a charge and I pull it from the negative side over to the positive side. I have to do work to pull it over there. So as I pull it across, then if it was 1 coulomb of charge, and if there's 1 volt of potential between these, I would have to do 1 joule of work to pull that over. And then if I let go, it's going to do 1 joule of work as it goes back over to the other side where it wants to go. Okay, so that's 1 volt. Okay, we'll see a little bit here. This one, of course, has a metal wire inside of it, and that's why charge can move very easily through it. Okay, let's take a look at some other things that we might have here. Okay, here is well, you'd probably tell me this is a battery, right? And you'd say this one's a battery, and you'd say this one's a battery. What's the difference between these? Okay. Well, let's take a look. So, how much potential? There's a potential. This side has a plus sign, this side has a negative sign. So we say there is a potential across here. So how much potential do you think one little battery like this has? How many volts do you think a battery like this has? So I've got a little meter here, and if you can see, 1.5 in a little bit. So about 1.5 volts. Okay, so this little battery like this has about 1.5 volts. What do you think if we went up to a bigger one like this? This one says positive and negative. So let's try this one. This bigger one, the AA. Oh, 1.5 volts. Well, how about this bigger one, the C battery? How much is that going to have? 1.5 volts? Okay. So these all have 1.5 volts. So what's the difference? Like, if I had something that took a C-sized battery, what if I put a AA-sized battery into it instead of the C-sized battery? They're both the same length. Actually, I could do that. I could put this in and it would work. It has the same voltage. It has the same amount of pushing the electrons through. So that would work. We say these are batteries, but actually the 3 that I have in my hand here are not batteries. These are electrochemical cells. This is just one cell, and this is one cell, and this is one cell. Can you think of any other meanings for the word battery? You hear battery in any other place? When we take standardized tests at ICS, lots of times at the beginning in the instructions we say, you will take a battery of tests. So a battery means a group of things. So this and this and this are all just one cell. But if we put a bunch of these cells together, then it will be a battery. There are rectangular batteries that are 9-volt batteries, and they have a number of these cells. So if an electrochemical cell has 1.5 volts to it, a 9-volt battery, how many electrochemical cells do you think are inside of it? Well, we got 1, and 2, and 3. So there's altogether, we'll have 6 of these electrochemical cells all wired together. So this has 1.5 volts. If I put the negative side of this one to the positive side of this one, now I'm going to have 3 volts across from here to here. Okay, so for voltage, we're only concerned about the difference from one place to another. And you can use this in different places. Sometimes you can, one trick I've learned is wiring up cooling fans in a computer. If you want to have it go a speed that's not the normal speed, you could choose, usually if it's a 5-volt fan, you can go from the 0 to the 5. But there's also a 12 volt in there. So if you wanted, you could take it from the 5 to the 12, and then there would be 7 volts across there. Okay, so these are our volts. So you can hook them together and add them up. You can also take these and put them together inside a battery. Car batteries are batteries, not just one cell, but they have a number of different cells. Those would be wet cells, we call them, because they have liquid inside of them that allows the charge to flow. So let's come back over here to our little friend here. Okay, so I put a wire on here and it traveled along just fine. I could also just touch them together and the flow of electricity would go from one side to the other. I could put a metal bar on here and it could go through the metal bar. What about the air? Is the air something that electricity moves through easily? No. Actually, air is a pretty good insulator. So our metals are conductors, but plastic and rubber and the air are insulators. Okay? So if I got a big enough potential difference, if I got a big enough voltage here, do you think I could get electricity to actually flow through the air even though it's an insulator? Well, let's see. I'm going to move these apart and can you see those little sparks? It works. Okay, so if I move them even a little further apart, let's see what happens. We find that if they are a centimeter apart, that's not quite a centimeter yet. Okay, so if they're a centimeter apart, it takes about 30,000 volts to make electricity jump 1 centimeter. Ooh, but here we are. There it goes. So 1 centimeter, 30,000 volts. Can we do about 2 centimeters? Even more. Okay, so this has a huge voltage between these. Here, I'll discharge it a bit. So as it's going, it builds up a big positive charge and a big negative charge. There's a huge difference, and it has a lot of force to push charge around. Okay? Just a couple of other things with this. If I put my metal bar here and I do this, am I in danger right now? Well, no, because my hand is not a very good conductor compared to this metal rod. So even if I was holding it over here, it's going to want to jump through the metal, not through my hand. So I don't get hurt there. All right. So then we mentioned resistance because we were calculating it, and resistance is going to be, the thing that slows down current as it goes. So Sometimes we add in resistance with resistors, and everything has some resistance, but conductors have very low resistance. Insulators are going to have very high resistance. But as we saw, even a good conductor like the air, if you get a big enough voltage, it can still overcome that high resistance and it can still push charge through. So, just one more thing that I'll mention is superconductors. Superconductors, you can start a charge flowing in a superconductor and it will just flow and flow and flow with almost no resistance. So superconductors are interesting things. They can do some interesting things. Levitating trains can use superconductors to make magnets that can make the train float along. So these are a few of the things that I'd like you to see about our electricity and electric current, how it is that things flow. All right, so if you have questions about these, you can ask me, and we'll leave it there.